Hello, this is the third video in a series about the eigenfunctions of Fourier transform. In this video, we will talk about the eigenvalues of the Fourier transform, and we'll talk about some kind of ideas that end up being generalized later if you learn about spectral theory for bounded operators on Hilbert space, for instance. However, for the Fourier transform, that would be much simpler because of this nice identity here. So let us talk about that. So recall that f squared is n. And what was n? N was this operator that took f and it kind of put a negative sign on the inside of x. And you can see the earlier videos in the series for more about that. We showed that n squared is I, the identity, and that's just kind of clear. If you do n twice, you can just get f. It just undoes itself. So because f squared is n and n squared is I, that means f to the 4 is the identity. Now this right here turns out that it makes the Fourier transform kind of act like a matrix, because you learn from matrices is that you have a matrix here that's like an n by n matrix. Then you have a characteristic polynomial, chi of a. I mean, it's not chi of a. It's chi of lambda, which is the determinant. I guess it depends on your notation, but a minus lambda I. And then this right here, from the Cayley-Hamilton theorem, it says that chi of a is equal to 0. So there is a polynomial that you could also show that kind of more elementary from just the fact that it's an n by n matrix. But the Cayley-Hamilton theorem tells you that there's a polynomial, the chi of a is 0. And there's also this polynomial called the minimal polynomial. It's a smallest degree polynomial. It is a smallest degree polynomial with p of a equals 0. And then from this, the characteristic polynomial tells you some things. The minimal polynomial also tells you some other things about the eigenvalues, about the multiplicity, and some other things like that. This right here tells us that if you have x to the 4 minus 1, p of x, some kind of polynomial, then p of the Fourier transform is 0. This is a polynomial that if you apply it to the Fourier transform, you get 0. So there's a lot of analogies here to this. It's just like here for the characteristic polynomial, just because you have a polynomial applied to 0, doesn't tell you what all the eigenvalues are. It can tell you what prospective eigenvalues are, but it doesn't guarantee what the eigenvalues are. We're going to see from this identity, we're going to be able to find out what the eigenvalues are if they could be something. And then later on in the series, we'll explain how you can get all the different eigenvalues and such. But let's just use this identity to see what the eigenvalues are, or what they could be. This fact that eigenvalues of the Fourier transform are plus or minus 1, plus or minus I. I mean, strictly speaking, what we're going to show is that these are the only possible eigenvalues. We're actually not going to show that they are all the eigenvalues, because we're not going to, we already showed that these are eigenvalues earlier in the series. We gave some examples. We gave an example with negative I as an eigenvalue, but we didn't really prove it. We just kind of said it was true. Later on in the series, we'll see the other values as well. So proof, let f, the Fourier transform of f be lambda f. So f is going to be an eigenvector, so eigenfunction, non-zero. Now you just, standard thing is that you do is you take f, you apply Fourier transform 4 times, because that's the identity. So this is the same thing as that. This right here, each time you apply Fourier transform to f, it picks up a lambda. So lambda to the 4 is f. And because f is non-zero, that tells you that 1 is the same thing as lambda to the 4. And then the only solutions to this are plus or minus 1, plus or minus I. So if you were to draw a picture, these are the eigenvalues. Now, let us write this thing called the spectrum of f. So what is the spectrum of f? The Fourier transform. The spectrum is defined to be the set of all complex numbers so that f minus lambda I is invertible. Is not invertible, so the inversion does not exist. So for a matrix, if A is a matrix, and if lambda is an eigenvalue, then a minus lambda I, the kernel of this is non-zero. And that just comes from the fact that there's an eigenvector. If you plug an eigenvector to this, you get 0. So the kernel is non-zero, and knowing that a matrix A minus lambda I has a non-zero kernel means that its inverse doesn't exist. However, with operators on infinite dimensional spaces, having an inverse existing or not is way more complicated than just knowing the kernel is non-zero in general. However, for the Fourier transform, it turns out that that's actually all you really need. You just need to stay away from those eigenvalues in order to be sure that the inverse exists. It comes from the fact that it satisfies this nice polynomial equation, and so in a certain sense, it kind of behaves like a matrix. And the fact that it's normal, but some technicalities, I guess. So let's go through this. So this is the definition. What we showed is that these are prospective eigenvalues. We didn't even show that these were the eigenvalues. So what we expect to see is that this right here is just plus or minus 1 plus or minus I. However, let's just read the notes. So if we define this as the spectrum, then using only the fact that f is unitary, this is kind of like a standard fact of bounded operators, the Fourier transform is going to belong to the Fourier transform. The spectrum of the Fourier transform, because it's unitary, is going to belong to the unit circle. So if I have a complex number here, z, in here, its length has to be 1. Those are just the rules based off the operator is unitary. And it'll kind of follow from some of the arguments we do a little later. I can show it using that kind of stuff. However, using the fact that f to the 4th is identity, you can show, using this identity, what we're going to show in these slides is that this right here is definitely a subset of plus or minus 1, plus or minus I. So it can't have anything else besides plus or minus 1, plus or minus I. The roots of x to the 4 minus 1 is equal to 0. However, showing that plus or minus 1 and plus or minus I are actually in the spectrum will involve some other things. And like I said, different than the way it is for bounded operators, it turns out it's just going to be related to the idea of eigenvalues. So we're actually going to show that these are actual eigenvalues. And that will show equality. In general, these things contain more than just eigenvalues. For a general unitary operator, with the Fourier transform, which satisfies this property, this turns out to just be the eigenvalues. So note, you can actually write down what the inverse is. So this inverse here, I wrote it here with omega instead of lambda. If you have omega, which is not equal to plus or minus 1 or plus or minus I, then you can actually write out what the inverse is. And you can then check that this thing is the inverse, which is kind of nice. And this right here, this identity right here proves this inequality here. Because if I have an omega that's in here, that's not one of these things, then I can write down the inverse. I mean, so it can't be in here. So the only things in here are the ones where this thing doesn't make any sense, which is these things right here. We'll derive this a little bit later, but I just wanted to say that it actually comes from the fact that we have this nice polynomial equation here. You can use this polynomial equation to derive this inverse equation. So, given what we have, we're actually going to make some assumptions. We're going to kind of assume that we're going to say E lambda is going to be the orthogonal projection with range equal to the lambda eigenspace of F. So F has eigenvectors, and the lambda eigenspace are going to be the subspace of all eigenvectors, and we're going to call E lambda the orthogonal projection onto that subspace. So an orthogonal projection is just a projection that is Hermitian. that satisfies this equation. Now, any subspace has an orthogonal projection, a unique orthogonal projection. The point is that the projection is kind of like a nicer projection. So for instance, a non-orthogonal projection would be a subspace here where any vector in this line stays the same, but then I take vectors up here and I kind of swash them down this way. This is not going to be an orthogonal projection because there's kind of like a skewing. Orthogonal projection, I would want things that are, if these are the things being fixed on this line, then I want things to be orthogonally projected. No projecting kind of in a way that's parallel to the thing I'm projecting onto. And that's reflected in this identity here. Okay, so I mean that's kind of the idea that I didn't write exactly correct accurately, but that's the idea. So what am I trying to say? So yes, I have this orthogonal projection here. It's the definition. Now the spectral theorem says in general that if you have some kind of spectral projections and you have the eigenvalues, then the operator, if it's normal, you can write it as some kind of integral or sum of spectral projection times the eigenvalue. Because there are only 4 eigenvalues, then this is 1 times E1 minus E negative 1 plus I EI minus I negative I. And that is kind of like a standard kind of definition thing, spectral theorem. By the functional calculus, which I kind of have to explain what that is. The idea of functional calculus is that you look at the spectrum here, which has these points. And what you do is you say that any function on the Fourier transform, so you have some kind of polynomial maybe, some kind of function. For polynomials, it turns out to be true. But if you have just kind of continuous function on Fourier transform, it turns out that you only need to know what f is at these points to determine what this is. So if I have 2 other functions that have the same values at these points, it gives me exactly the same function of the Fourier transform. So why is that important? Well, the reason is that what is a spectral projection? Spectral projection, you could think of it as a characteristic function on lambda. So you're thinking of it as a function that is 0. So it's 0. So let me say of z. It's 0 when z is not equal to lambda, and it's equal to 1 when z is equal to lambda. So it's kind of like a characteristic function. And the spectral projections, as far as spectral theory is concerned, is that this spectral projection is this characteristic function on the Fourier transform. It's a function that's 1 on the certain eigenvalue, lambda, and 0 everywhere else. Now, because the Fourier transform only has 4 points in its spectrum, plus or minus I, plus or minus 1, all that I need is a continuous function, p lambda, so that p lambda agrees with the characteristic function on the spectrum. Then p lambda of the Fourier transform will be the characteristic function of the Fourier transform, which is the spectral projection. So, I mean, where would I get this kind of p lambda from? Well, I mean, x lambda of f is the function that is 1 on lambda 0 or else. Now, it turns out that chi of lambda of z is chi of 1 of lambda inverse of z. Because think about it, right? If you put lambda in here, you get 1. If you put lambda in here, the lambdas then cancel, it gives you 1. So that checks out. And then as far as characteristic function is concerned, if you plug in something in here that's not lambda, this will be 0. You plug something that's not lambda, this won't cancel to be 1, and so you get 0. So because this identity is true, this identity is then true. And so, what is characteristic function of 1? Now, this function right here is not the Fourier transform. However, it has the same spectrum as the Fourier transform. The reason is that lambda inverse, I'm picking lambda. I don't know if I say it here. Yeah, lambda is an eigenvalue. So lambda is plus or minus 1, or plus or minus I. And if I take the spectrum of f and I multiply by lambda or lambda inverse or whatever, it turns out that it just kind of rotates these. And so it doesn't actually change the set at all. So this right here is the same thing as this. Now, what is characteristic function 1 on this? So I want a function z that is equal to 1 on 1 and 0 when z is not equal to 1. But only for the z, we only need to care about the z's that are plus or minus 1 and plus or minus I. So it comes from this function right here. I don't know why there's a 4 here. It should be a 3. So 1 plus z squared plus z cubed. And then I divide by 4 just to normalize it. So if I plug z equals 1, p of 1, well, it's 1 plus 1 plus 1, you divide by 4 is 1. If you have p of negative 1, then what happens? You get 1, negative 1, so they cancel. 1, because negative 1 squared, negative 1, because negative 1 cubed. This is 0. What is p of I? Well, it's 1i, negative 1, negative I. So 1i, negative 1, so these cancel. I, negative I, they cancel. And then you can also show that p of negative I is also 0. Now, there's a nice symmetry property here. So summing roots of unity. So a root of unity is some kind of number to an nth power equals 1. So I is a fourth root of unity. It satisfies this property here. Negative I also is the same thing. Negative 1 is also a second square root of unity, but it's also a fourth root. Its fourth power is 1. So this kind of expression here, if you take this, you can factor it like this: 1 minus z to the fourth, 1 minus z. Well, it's not really factoring it. You factor this numerator here, and then you divide, and you get this. So as long as z is not equal to 1, this thing is equal to this thing divided by that thing. In particular, if you plug in plus or minus 1, plus or minus I, you just get this characteristic function. You plug in 1, it gives you 1. That's this. Or I guess I should divide by 4. If you plug in anything that's not 1, then this thing won't be 0, but this numerator will be, as long as it's plus or minus 1, plus or minus I. So this is p of z. This is going to be a characteristic function here on the set plus or minus 1, plus or minus I. And so what you can do is you can just plug lambda inverse of f into it. Just into here. So the 1 becomes I, z becomes the function, z squared is this, and z cubed is this. So we have formulas for the spectral projections of f. It's just these things right here. What you can also show is that f, remember f is some lambda e lambda. Well, this is the spectral projection for 1. That's E1 times 1. This is negative E1. I mean E negative 1. This is I, EI, and this is minus I, E negative I. And if you want, you can show, so this is the spectral decomposition. This right here projects onto the eigenvectors with eigenvalue 1. This projects onto the eigenvectors with eigenvalue negative 1. This projects onto the eigenvectors with eigenvalue negative I. This projects onto the eigenvectors with eigenvalue negative I. You can also show, I mean, if you want, you can actually just expand this and check that it's true. So for instance, we have I over 4, negative I over 4. I times I over 4, negative I times I over 4. So there are no i's. See, there are no i's over here. What about f? F over 4, negative f over 4. So that's positive f over 4. I, negative I f over 4. So that's the i's and the negative I cancel. Negative I f over 4. So we get f over 4 in all of these. You get 4. I mean f. If you do f squared over 4, negative f squared over 4, they cancel. Negative I f squared over 4, negative I negative f squared over 4. So they cancel. So there are no f squareds. You can do the same thing with f cubed. The point is that this is definitely an identity. It comes from the spectral projection, spectral decomposition. And we got those by writing the spectral projections using the functional calculus. We found a function that was 1 on the eigenvalue and 0 everywhere else, and then we expressed f as that. You can also check that this right here is a projection, so we can actually check that. We didn't actually show that, but it doesn't hurt, right? So if we took this thing and squared it, it's gonna kind of be a mess. So I'll just expand this thing out really big. So this is 16 here. Now squared. So we have I times I, that's I. How do I want to do this? So let's collect all the I terms. So remember, f to the 4 is the identity. So I times I is I. F times f cubed is I. F squared times f squared is I. But also f cubed times f is I. So there's 4 ways to get I. Okay, now we'll erase these, and we'll say those are 4i. Now what about the f? So how do you get f? Well, I times f, and also f times I. Now, in order to get an f from these other powers, we're going to have to use the fact that f to the 4 is f. F to the 5 is f. So that's this times this, and this times that. So we found 4 ways to get f. Now, what about f cubed? F squared. The way to get f squared is to get 6. So f squared, there's 2 ways to get it like this. You just multiply this one way and this the other way. So it's 2f squared. And then also 6 power. Well, that's this times that. You multiply by itself. So that's another 1. So there's 3 so far. And we need f squared, which is also this thing squared. So we get 4 ways to get f squared. What about f cubed? Well, you can get f cubed. It's the same thing as f to the 7. But you can't really get that in these 2 terms. So we're just going to look for f cubed. How do you get f cubed? F cubed times the identity. Or let me erase these. You can do identity times f cubed, and then also f cubed times the identity. Also f times f squared, and f squared times f. So it's 4f cubed. And you see you have 4 here and divide by 16. So it's I plus f squared plus f cubed all over 4. And you saw this thing squared is itself. So that means it's a projection. This thing, E1, is a projection. We didn't show that they were orthogonal projections, which was that E1 star is E1. However, that is a straightforward fact from the fact that f is unitary. So f is unitary, which means that this is its inverse. Because f to the 4 is identity, its inverse is actually f cubed. So its adjoint is f cubed. So if you do the adjoint of E1, let me erase this so I have some space. E1 adjoint. We have I adjoint plus f squared adjoint. Okay, so I adjoint is just I. F adjoint is f cubed. F squared adjoint, well, Well, it's f adjoint squared. F adjoint is f cubed squared, which is f to the 6. And using this, that's f squared. Now, what about f cubed adjoint? Well, it's f adjoint cubed, which is f to the 3 to the 3, which is f to the 9. And then using the fact that f to the 4 is the identity, that's f to the 8 times f. And this is the identity, so this is just f. So you see here that E1 adjoint is just, these are just the operators just in a different order. This is E1. And it turns out you can do the same thing with E-1, EI, and such. The fact is that E1 is projection onto the eigenvectors of F. Because F is normal, it turns out that because these things are polynomials in F, so this is a polynomial in F, this is a polynomial in F, then E1 is also going to be normal, EI, E lambda are going to be, these are all normal, and they're projections. So a normal projection, turns out it's going to be an orthogonal projection. That's just a fact. So we've kind of used the spectral projection idea. We've expanded it. It's a little abstract if you're not too familiar with the spectral theory. But the idea is you're thinking of a diagonal matrix. You have a matrix that has some eigenvalues. Now, if you want to have a function that's a projection, this right here is a projection onto the eigenvalue, the eigenvector with eigenvalue 1. Now, what you would do is you have some kind of function f, or it's called p, a polynomial that is 1 on this and 0 for all the other values. And that means that P of A is going to be the spectral projection for lambda 1. That's what you kind of want. That's kind of the idea. And it turns out that we want to also generalize that for general operators on infinite dimensional spaces. However, you can't always do that because the spectral thing is often difficult. Sometimes it contains infinitely many points. Sometimes it's not just infinitely many points. Sometimes it's a continuum, and so there's all these technicalities. But turns out because f to the 4th as the identity, you can just do the same kind of stuff. You can do the same kind of stuff that you would usually do. But you have to be a little bit more careful. And I just wanted to express some of these ideas in terms of functional calculus, which is related to spectral theory. And these things are written in ways that look like the things that you would learn if you took a functional analysis course. That's the point of this exercise, is to express things in that way. So now that we've done that, I wanted to at least mention this identity that we had up here, because I showed the inverse was true. So this right here, identity, is kind of like an algebraic thing. This is kind of an interesting thing. Way we derive this identity is to use some formal power series. So proof of the identity. So we use an old trick of expressing this thing as 1 plus x squared plus x cubed, etc. So this right here is true. So this converges as long as absolute value of x is less than 1. So if you want to find some kind of formula for this right here, where x to the 4 is the I1, which x here is, we're going to think of it as our Fourier transform, basically. Because we're doing some formal power series, we're not going to write f in, but we're going to get an identity at the end of the day, and then we're going to say this identity should probably be true for the Fourier transform because it satisfies this. However, what we're going to be doing is kind of going through formal algebraic stuff, passing through the land of, well, that's probably not convergent. But we'll get something at the end of the day, which is true, which is going to be universally true. So it's kind of like this interesting idea that if I get some kind of identity that holds on on some kind of interval where it converges, it's kind of like a homomorphic thing that you get for analytic functions. If you get some kind of identity that you know holds using some kind of infinite series stuff or whatever, then it's going to hold by analytic continuation everywhere where they're defined as analytic. That's kind of the idea. Suppose we have this x minus omega inverse. You have omega to the fourth is not 1. So omega is not one of those values, plus or minus 1, plus or minus I. And we're going to use formal power series to try to express this in a nice way. So first, what we're going to do is we're going to factor out the omega. So we're going to divide by omega, multiply by omega, and then pull this omega out. So this omega comes out as an inverse, because there's an inverse here. And this becomes omega inverse x, and then minus 1. So now this right here looks kind of like this. So in order to exactly write like that, we're going to pull out a negative sign. So negative omega inverse, 1 minus omega inverse x inverse. And now we're going to use the formal power series. So negative omega inverse, this is 1. This is plus this, plus its squared, plus the cube, plus the fourth, plus the fifth, sixth, seventh, etc. Oops. So now what we do is we want to use x to the 4 as the identity. So what we're going to be able to do is group some of these terms. So we have this 1, we're going to be able to group it with this because x to the 4 is the identity. So x minus omega inverse is this negative omega inverse. Now I'm going to group all the powers of x to the 4 because x to the 4 is 1. That means x to the 8 is 1, etc., etc. So we have 1 here, omega to the negative 4, omega to the negative 8, etc. So those are all the x to the 4 terms, or just the 1. These are just 1s. Now, the x terms are going to be x to the 5, add 4 to that, x to the 9, etc. So I have x here, x to the 5, x to the 9. So I'm going to have omega inverse, omega to the negative 5, omega to the negative 9, etc., times x. Times x squared, it's just going to be 1 up. So you see it every time. So here we have omega inverse is x squared, but then also add 4. So negative 2, negative 6, etc., etc. What about cubed? Well, the cubed has this, and then I add 4, add 4. So negative 3, I add 4 to the 3, not 4 to the negative 3. Anyway, so this is the expressions that we get. It's just formal power series. Now what we're going to do is recombine them to get rid of the formal power series. And I get this. So at this point, this right here and this thing right here, these are now things that make sense for all x that are not equal to omega, and omega is not equal to, as long as these denominators make sense. And I got rid of this assumption of formal power series. However, as rational functions, they should be identical because rational functions, if they are valid on some small domain, on some small little disk, where this convergent power series stuff should work, then this should be relevant identities. They should be the same, as long as I'm assuming that x to the 4 is 1, because that's what I used in this collection of power series. Anyway, so what is this? This is 1. This is the same thing as 1 plus, let's say, a plus a squared plus a cubed plus, it's 1 minus a inverse. So this is omega to the negative 4. That's down here. This is not quite that, but if I pull out an omega inverse, then it just becomes this. So omega inverse times that. Here I can pull out an omega negative 2, and it's just that. Here I pull out omega negative 3, and it's just that. And then there's an x, and x squared, and x cubed. There's this thing on the outside. So what I can do is I can factor this x there in all the terms, and I get this. Now, I don't really like this kind of nasty expression in the denominator. So I'm going to multiply by omega 4 and negative 4. And I also don't like that there are negative exponents everywhere. So multiply by negative 4 and negative 4, omega to the 4, omega to the 4. Then this omega 4 here makes this omega to the 4 minus 1 in the denominator. This omega to the 4 up here, well, I can take one of them and hit here. So I get negative 1. And I put 3 of them in here. Omega 3, omega squared x, omega x plus x cubed. And this should equal x minus omega inverse when x to the 4 is 1. So this should be just some kind of algebraic identity. It should hold in some very abstract algebraic sense. So basically, I should be able to take this thing, expression here, multiply by x minus omega, and use this to get inequality. And it should hold algebraically. It shouldn't matter whether or not x is in some kind of interval or whatever for convergence or whatever. Now you can check that. Do I do that? I don't do that. So I mean, I might as well check it, right? So got the time. So I just need to show that x minus omega times that gives me 1. So let's do that. So x minus omega, I'll distribute the x. So I'm just going to increase the x term on all of these. There should be a squared here. And then put the omega in, minus omega to the 4 minus omega cubed x minus omega squared x squared minus omega x cubed. And what do I need to know? I need to know the x to the 4 is 1. So this is 1. So let's group the terms, right? So we have the constant term, so 1 minus omega to the 4. Now let's group the x terms. We'll group the x squared terms. We'll group the x cubed terms. So x is omega cubed. X, I'm looking for another x, minus omega cubed. X squared is omega squared. Like minus omega squared. X cubed is omega. X cubed minus omega. So we see is that this cancels, this cancels, this cancels, and I'm left with this thing divided by its negative with a negative sign. So it just gives me 1. And then what you can check is, okay, this definitely is going to hold for f equal to Fourier transform. So I'm going to take x, replace it with the Fourier transform, and it's just going to hold. I mean, all these identities, it's just pure algebraic identity. So I can just plug f in, and then it's going to be true. You can just check it if you want, but you can just see it. I didn't do anything weird. I just kind of assumed the x omega is omega x. I mean, if omega is a number, then you can do that with a multiply by a Fourier transform. Or if you're thinking of omega as omega times the identity, then they definitely can. So anyway, in any case, we get this inversion formula. Where is it? This inversion formula here. Kind of a nice inversion formula. Another way, actually, you could find this inversion formula, which I didn't. Let me just finish the notes before I go off on a digression. So the series expansions are valid for this certain thing. We get this thing. That's what we showed. We have yet to show this. We kind of claimed that negative I was in sigma f in the first video. I gave an example of this right here. And I said that this was negative I times that same function. So I'm claiming that negative I is in the spectrum. However, I didn't show it. I mean, that's one thing. Note, we can verify the identity directly. That's what we just did here. We verified that the equation was true. One thing I wanted to mention is that you can actually get this identity in a different way. This identity here. Because all that you need, this is just a functional calculus thing. All that you need, what do you know here? This is some kind of continuous function. This is like f of lambda. And what is f of z is 1 over z minus omega. It's a function. It's just a continuous function on the complex numbers. It's not defined at omega equals z. This function here it's not defined as omega equals z, but the omegas that I'm not allowed to pick first. So the z's are basically going to be the things in the spectrum. So I definitely want omega to not be plus or minus 1 plus or minus I. Basically, if I'm thinking of f as being all the possible values of z, the spectrum of f, sorry, I'm thinking of z belonging to the spectrum here. That is where there should be problems with inverting, because that's when the inverse doesn't exist. So that's what I'm thinking of this function on that set. Now, this right here is a polynomial function. This is a polynomial function in z. And what do I need? I need p of 1 to be, there's an omega here, so if omega is fixed, omega is not equal to one of these. And this is the function, so I need to plug in 1. P of 1 needs to be 1 minus omega. P of -1 needs to be -1 minus omega. P of I is I minus omega. P of -I is 1 over -I minus omega. So I need some kind of polynomial that does all this. And it turns out that this right here is going to be, if I think of P of z as 1 over omega to the 4 minus 1, because remember, this is just a number, and I'm thinking of it as a function of z. It's going to be omega cubed plus omega squared z plus omega c squared plus, oh, I don't think there should be an omega there. That's a mistake. Plus z cubed. And you can see that when I check it. I don't have an extra omega here, so this is a mistake. There's an extra omega. Typo. There should not be omega here. So, this right here should be my polynomial that satisfies all these properties. And I could check that, at least one of them. Let's check P of 1. I mean, you could use polynomial interpolation, right? To find out what P should be. However, let me just check that this is true. P of 1, if I plug 1 in, omega to the 4 minus 1. 1 is omega cubed, omega squared, omega plus 1. Now, what you can check is this is just that identity again. Now the sum here becomes 4th power minus 1, omega minus 1. These cancel, and I get 1 over omega minus 1. That's not exactly this. They're flipped. So am I forgetting a negative sign or something? Z minus omega inverse, that's this function here. Looking 1, so 1 for this. Negative the 4 minus 1. There's some kind of negative sign off. Let me first make sure I have the right formula. So the formula that I checked had a -1 sign here. Negative 4 minus 1. Am I missing that on is the formula also have another typo? Yeah, I think this should be 1 minus omega 4. Because when I checked it, it had a -1 here. Yeah, so it definitely needs a negative sign. So that's why when I checked it, so negative sign here, negative sign here, and then these things cancel, they flip, which is 1 minus omega, which is exactly this right here. And then I bet you check these other ones, they'll all be true too. Because that is what this needs to be true. This needs to be true. I mean, and this is a cubic polynomial. And so you can't really have any other polynomial that satisfies these conditions. That's a cubic. As far as omega to the 4 is 1, because If you had a higher degree polynomial, then they all get reduced to a smallest degree 3 polynomial. Just a minimal polynomial idea. It's related to the minimal polynomial. Anyway, so yeah, I wouldn't want to actually find P from this. However, the method that we used earlier to find it using the formal power series is really nice. So anyway, so this is a long discussion. So the idea was that we took this right here, which we derived kind of from simple considerations. We found the eigenvalues, and then we said, well, there are some other things that people do in functional analysis related to spectral analysis and stuff. Let's show that that abstract set, this spectrum, is the same thing as the prospective eigenvalues just from this identity here. We didn't even use anything else, and the fact that it was unitary. The unitary was used for things related to the spectral projections, but as far as the spectrum is concerned, we just literally use this identity here. Spectrum here will show you that everything is fine. Seeing this identity, using the fact that F was unitary, we think we can get the spectral projections are self-adjoint or the Hermitian just from the fact that F is unitary, but this kind of decomposition also again comes from this. Or not that exactly. Because you can still define these things in terms of it's kind of polynomial function. And you can still check that they're projections. That's what we checked. We checked that this was a projection. However, the fact that it's an orthogonal projection comes from the fact that F is unitary or normal. So normal is the more general property. Normal operators are that kind of operators that people care about and like all the time. So that's the end of this topic. It's kind of like a digression because we're going to pick up some of the similar ideas when we do symmetries and I'm using group representation, and it's going to be a lot simpler. So we're going to get some of the same results, but it'll be simpler, and it'll be expressed in terms of the idea of spectral. I mean, in terms of eigenfunction stuff. This was a little bit more abstract. So that ends this video, and we'll continue on with the next one.